Diese Konferenz wird nun aufgezeichnet.
And so we will present our work, of course, and this is, I'll show you the agenda of this meeting. So after this short introduction, we have a general overview about the type of train consistent, the type of problem that we want to solve with Marathon2 operation. Then we have a presentation on the radio solution. This presentation will be held mainly by Ball because the colleague from Fonquer could not attend today, unfortunately. Then we have a presentation about the simulations.
Diese Konferenz wird nun aufgezeichnet.
To these questions, and if there is time, we have also the possibility to interact. Then we have a break, and then we have a look towards the future. So the implementation of what we have found as possible solution for implementation for the market. And then we have also a sharing of the future applications of this research from Niels Weigel. So the meeting will be recorded, and if you think, Christine, is now the time, we can try to share the videos, and we can try to have a screenshot. So for the participants, we are not the full number, but as we said already before, some of the participants will connect just to attend to the parts of the presentation on which they are more interested. So now I stop my sharing. Maybe Christine, could you share your screen because otherwise I don't know how to. No, maybe I interrupt the presentation, okay, and I will put this here. But I don't know how to show all the participants. No. So yes, okay. This here.
Nope. Yes. You could have left the agenda, perhaps, if you want, and we leave it with the picture. But see if you can take it off, then it's okay too.
Okay, so please.
Sorry?
Okay. Could you take the picture?
For the moment, I don't see a lot of cameras. And if it stays like that, perhaps you should put the agenda because it looks nice with the picture. Okay. Because here I have your picture, which is nice too, but
okay.
Yeah, that's great.
Okay, so sorry for this. And now I give the floor to Andrea for a welcome.
The picture is not done yet because I'm waiting for the people to turn on the cameras. Sorry.
Okay, so maybe I think it is good if we do this in the meanwhile. I don't know if Andrea can take the floor. I don't see him now.
Yeah, do you hear me? Good morning. Hello.
I hear you, but I don't see you. No problem.
I see myself.
Yes, I see you, Andrea.
Yes, okay, now I see you. Sorry, you are in the corner.
Okay, good. Very good. Okay. Good morning, everybody. This is Andrea Mazzoni speaking. I'm the coordinator of Shift2Rail Freight Rail 2. I am working for Bombardier Transportation, and I'm representing Bombardier Transportation in IP5. And I'm really happy to be here and to give just a short hello and to talk about the project Long Trains, a project that has started early in Shift2Rail. So it's not only Marathon as such, but we started with FFL4E. That was one of the first Shift2Rail projects in IP5 that the first one that started to deal with long trains. The vision is clear. The vision is we want to be able to run long trains in future up to 2,500 meter lengths, and this including multiple traction. And how we did that in IP5, in the multi-annual action plan as well, we defined a strategy, or we defined the various steps towards this vision, towards this goal. And as I was saying before, FFL4E was the first one. There we successfully demonstrated the remote control of a second locomotive, not using a dedicated radio transmission, but relying on GSM-R and using basically a WTB similar communication. You may know WTB, the wire train bus. So it's a standardized protocol for used, widely used for multiple traction, and we implemented this on the radio transmission. It was a short train, 500 meter long, but with 3,000 tons, one locomotive at the end, one in the front. And now with Freight Rail 2, we are continuing. We're doing the next step. We're adding an additional locomotive, another type of locomotive, and we are using a new communication system. We rely on LTE, looking also forward to FMRC, so the new standards that is upcoming. And as Luciano was saying, being the complementary project to M2O, in this case, we're working together. Having long trains means also having a lot of challenges with respect to the longitudinal forces, to how the train is being composed, how where the wagons are standing, the heavy ones and light ones, etc. And I strongly believe that the work that has been done by M2O so far allows us to go the next step. In Shift2Rail, we will have a next step. We will have another project that is going to build on the results of Freight Rail 2, on the results of M2O, towards the vision and the goal that I mentioned before. So, Luciano, I would like to thank you and the whole consortium very much for the work that you have been doing. I'm looking forward to the final results as well, and it will be glad to have you on board also later on in whatever way this will be possible. Let's see, and continue this journey together towards remote controlled distributed power for long trains. By the way, just one very fresh results. We tested this week for the first time the connection between 3 locomotives. The 3 locomotives we will use for the demonstrator in February. Traction and brake control has been working well. We did some static and dynamic tests, moving the locomotives just a few meters. But I'm sure Niels will talk about that more in detail later on. So very good results, and we're really looking forward to the demonstrator in February. Thanks again. Wish you a very good final event, and all the best.
All the best. Thank you, Andrea. Now, I want to leave the floor to Niels, with whom we worked really side by side in these 2 years, because we confronted each time to check the progress of the project. So please, Niels, the floor is yours.
Yeah, hello together from my side too. Niels Weige, DB Cargo Innovation Management. We are together with DB Nets leading all the Shift2Rail long train projects since FFL4E time. And as Andrea mentioned, we are very glad to make now the second step in going this way to 1,500 meter trains. I will show some slides at the end. So I would give the floor back to Luciano and to the M2O project.
Okay.
Thank you.
Okay. Very well. Okay. So now I give the floor to Armand Toubol, who, as I say, is technically coordinated with me the project, and Armand will give an introduction about the type of problems that we can solve with this new technology. Armand, you will share yourself the screen? Or
yes, I have the screen shared. If you can see it, it's okay?
Yes. Okay.
So we will start straight away. I am Armand Toubol, former freight director of SNCF in the past year, some years ago, and here I have been the technical coordinator for this project. Well, I won't enter immediately in the core of the subject, because effectively, why do we do marathon trains, this long train with distributed power? It is because in front of us we have seen the development of the road very quickly, and which has created gigaliner. And some years ago in a conference, I was saying that if we have the road with gigaliners, we would need gigatrains. It's not so easy to have gigatrains in Europe, and the small map you have on the right shows how many difference you have all across Europe, certain times only on certain itineraries where there are possibilities. So this is the starting point. The second fact is, what are the market segments? Because effectively, when we make such a project, it is important to start from that. In fact, we have three main market segments. The first one is the bulk. The bulk transport is still the favorite market of the freight, and for that reason, what is important today is to continue to make progress in terms of cost reduction and efficiency. The second growing segment, which has a high potential, is all what deals with containers, swap bodies on short, medium, long distance, because we have tremendous traffics starting from the ports, starting from the clusters of industry, and which are European transport. And this is a very large chunk of the traffic, which is very fastly growing, which needs frequency, adaptable capacity, reliability, and cost reduction. And when I say adaptable capacity, it's to find that capacity also on the network. The third market, which has been suffering quite a lot, was the general cargo segment, which was the single wagon load. In certain countries, it has nearly disappeared, and there is a lot of efforts today to restart, to re-jump, to find a jump in this type of traffic. And it will be very different, but it needs cost reduction. It needs mainly reliability. Long distance, probably with consolidation and distribute from in consolidation place and distribution hubs. This is mainly a segment which is probably a big challenge, and we have to tackle it. So to face and to adapt ourselves to these various segments, there are a certain number of concepts that we have studied studied jointly with our friends of Freight Rail 2. And you can see in this picture the different type of distributed power trains, longer and longer, starting effectively from the first test that we have made in France with the two marathon trains to 1,500 meters, but with a specific radio communication, and building on Freight 4E, which was, as Andrea has described, some tests made in May 2019. Then we have all these possibilities in front of us, which will be developed later on. Finally, the main features of N2O, which we will develop progressively in this final event, we start from the standard characteristic of European traction units, involving exactly the type of TUs which are used in Freight Rail 2, which are the Bombardier locomotive 187, if I am correct. European wagons and loading distributions have been taken from a large database of German trains, representing largely European freight traffics, which are used to generate virtual trains according to UIC. Then you have the radio communication system, which I will present, missing the speaker of Funkwerk, who is unfortunately ill, and I am sorry for him, and I wish him a quick recovery. We have various also categories of infrastructure which have been introduced in the safety studies and the simulations that Luciano will develop. Safety studies and assessment implementation plan with use cases and a suggested roadmap. So this is exactly the situation at the beginning of this project. Luciano, I may switch immediately to the presentation of Funkwerk.
Yes, please. Switch to the other presentation, yes.
So just give me a second to...
And then, of course, if there are questions, you can answer later the presentation about
the question have to be put in the chat. So I am trying to prepare the second. Here it is. I have to share that screen. I share it. Okay, we are okay. I hope I can control it. So we will concentrate on the mobile network communication here. How can I? It comes. Okay. Of course, there was the beginning, and it was described by Andrea in a few words, saying FFL4E, future freight loco for Europe. AIM prototype of long train data transmission was based on GSM-R CSD calls. Radio modules were developed and provided by Funkwerk. Result of radio integration and performance in FFL4E, leading loco make a CSD call via GSM-R to guided loco. Guided loco receives CSD call. So you see, it's a permanent connection established. M2O started by analyzing results, and the aim was 15-meter long train with up to 4 loco. This is the description of the architecture, which is quite simple. Of course, there is all the inside of the locomotive. Then there is the connection with the radio command system by an IPTCom, and then it goes to the GSM-R and goes to the second locomotive. So you can see it's very simple and clear. And the problem is to have, we will see what are the problems that we can face. To achieve an abstraction layer, the radio communication is controlled by onboard IP network. Like concepts of FRMCS, the radio module CDPS, radio control distributed power, establish automatic link over a radio network. IPTCom is used to communicate radio link status changes and requests to establish or terminate the radio link, and it is used, of course, to transmit the payload between the train control management system of the locomotive and the radio. So we can see the problem. We have a latency in the GSM-R, not the latency, but with its pure transmission, but which is organizing and getting the connection. And then this has been tested in practice, in Funkwerk laboratory, to 750 milliseconds, plus or minus 30%. The latency between the train controller and the radio controller for both TUs end-to-end means that we have to add to that a certain time to make these connections inside. And on laboratory, we found that the overall end-to-end radio communication is 1.1 second, and that the test in FFL4E showed that, in fact, it was average 1.6 seconds. So this element is very important for the radio for the remote control of the locomotives. GSM-R has limitation, unfortunately, because when you use GSM-R, you use a permanent number of channels for more than two remote control locomotive. You arrive to 6 channels, and in certain places there are other traffic which uses that, and specifically ERTMS is using this sort of channels because it is a priority use for GSM-R. So as you can see also that we have to install 3 additional antennas on the top, and we have to install more modules inside the cabin. So it is pragmatically, it is impossible to have more than 2 TUs in the DPS, 2 TUs, 1 at the lead and 1 remote control. So we had to find a solution during the project. I will switch to the next slide. You can see here that we would have had to add 3 additional GSM-R locomotive and modules inside. So we thought that it was necessary to move. Each loco each traction unit is equipped with 1 additional radio module and CCPS and additional antennas on the lead locomotive. So the solution which has emerged rapidly for the partners of Freight Rail 2 and for us in M2O, it was absolutely evident that we had to switch to a system that would send packets, and we looked at what was available, which was LTE with a VPN and private APN, which enables to have effectively directly communication with the three remote control in the maximum 3 remote control locomotives. So we started to investigate LTE, and we looked that we were totally in agreement. Cooperation with Shift2Rail partner Freight Rail 2, joint development of IPTCom, because this is inside the locomotive of Bombardier, in case of locomotive of Bombardier, but in any case with any other type of locomotive. Layer concept addressing functional safety and IT cybersecurity, which is an important question today if you want to handle that properly. Integration of Funkwerk in Bombardier Loco, coordination of safety issues. So M2O Funkwerk was responsible for security layer in the radio, onboard integration, a standard IPTCom device without special security, radio link over LTE network using private APNs, separating traffic from other public mobiles, no direct communication between mobiles. It goes through a center of Funkwerk, and which may be tomorrow a center of FRMCS, for instance. Traffic is only forwarded to traction units which are registered to the same train number. Traffic rules are enforced by central application, that is the Funkwerk control center that I was quoting. Multiple train consists can be registered in parallel with separation of traffic. So if we have a look at what it looks like, this safety and security layer, you can see it from the leading loco to the guided loco. We have the safety layer, which is going from one CCU to the other and covers this sort of communication. Well, some information onboard integration of the IPTCom device. And what is interesting is that the cycle for the message, it takes 64 milliseconds. Latency limits are defined, real-time behavior. Safe state is entered after timeout of communication, radio link error to trigger, in that case, different mitigation attitude solutions. Funkwerk part in M2O, this is the summary of what they have been doing, creating the communication model, calculation of latency, measuring support the communication models calculation, development of this CDPS prototype hardware on board device, lab test. Tests have been made on site and not only in laboratory, providing hardware for lab testing and equipment, development of CDPS and development of its control. So the general layout is here where you can see the VPN, but it repeats what we have shown just before for the multiple locomotive control radio communication. So there is one thing which is important, is the setting up. The setting up of a long train, steps on each loco to set up a logical long train. It is an important part of the job. It is the part which it operates is good functioning after. Enter a train number. Oh, somebody has not cut his microphone and there are some other noise. Enter the train number, start the radio communication, wait for status ready, perform the initial test. Then automatic action start to take place, point 2 to point 3, register loco with engine number, train number and IP address forward traffic between already registered loco within the train consist. This is a very important part to be done when you start a GPS long train. What is interesting is that we have had laboratory tests, and the scheme of this laboratory test is shown there, and it is interesting to see that this confirms that the average latency over radio link would be 70 milliseconds, and the average latency between TCMS is about 390, which explains the way we have handled then the simulations. What is very important and which supports the choice of LTE is that beyond LTE, what is important is to understand that 5G and FRMCS are arriving in the rail world, and this slide shows that we have preparing step to this forward development, which will happen in the very near future. So I've been short as possible, leaving time if there are two questions on this radio communication. I hope that I have also the support of Jean-Michel Evangelou, who's the specialist of the development of FRMCS in UIC, and for the group, the European group dealing with that question. So many thanks for listening to that part of the presentation. Luciano, the floor is yours now.
Yes. So first of all, thank you, Armand, for this presentation. I don't know if Jean-Michel is connected, and if you want to
yes, I am.
About maybe the slide or about the work that we've done so far within M2O. Please, Jean-Michel.
Yes, thank you.
Thank you.
Hello, good morning, everybody. So now, what is interesting in that global application is that it's really a use case which it is I would say which is using the new capacities of telecommunication. So and there are a lot of them, which is important. You know, there was a lot of things done in GSM-R over the last 20 years. GSM-R is a very successful system, of course, for voice and communication, operational communication, I would say, plus signaling in a lot of cases, and ETCS particularly. But having said that, GSM-R doesn't have chance to reveal that it didn't have the capacity to have a lot of other applications like this one, for example. And really, this application is a good example of the thing we can do in a new world with a better capacity, better flexibility, better latency, and also more channels to communicate, because one of the blocking factors there was mainly the problem of channels, which is the circuit technology of 2G. GSM-R is 2G. So it's a very good example. So speaking of application globally, of course, for a certain period of time, probably this system has to be developed on existing network, LTE. But for some country, for a short time, because everything is ready, I would say, to be ported to FRMCS. And you may know that the 5G FRMCS system is under preparation, and that a lot of countries are looking for deploying their first lines in 2025 in Europe. So with a global plan of substitution, if I can say, of GSM-R. Of course, 5G, if I can say very simply, is even better than 4G by definition, but in fact it is really better. There is a lot of change between 4G and 5G is really a sort of mini revolution into the telecom world, not only for highway but for everything. And so that's the good news of this application. So it was conceived at the origin for GSM-R somewhere, but it has been capable to evolve during the project to look at other possibilities because of some blocking factors. And now it's prepared for the, I would say, the new set of railway telecom networks. So that would be my comment, very simply.
Okay. Thank you very much, Jean-Michel. So I do not see questions in the chat for the moment. So maybe I can say something about what Armand has very well presented. As Armand said, we started with GSM-R, and then we considered also LT. Of course, as also Jean-Michel said, you will see in the next results of my simulations, the simulations with Trend-I, that there are several options, there are several train consists that can be realized with 2 traction units. So for them, GSM-R is a very good solution, but you can increase the number of traction units and the length of the train, the hauled mass, if you think to implement also another technology. So the results of this project can be used, let me say, from tomorrow, but also from after tomorrow. Okay, so I think this is something good of the results of this project, but you will see the simulations, I will show you, and also Armand will show at the end the roadmap for implementation. We will speak about, again, about this different type of train consists. So is there room for, we have a space for room for a question if you want, otherwise we can anticipate the time, and I can take much more time to speak about the simulations in a relaxed way.
Okay, on my side, I have nothing specifically to add, just to say that in our project, effectively, we have started with GSM-R, we have studied LTE, but we have also given in the simulation and in the use cases that will be presented, we have also integrated the possibility and the characteristic of what would be offered by 5G, or what will be offered by a sort of specific synchronized solution, which we will develop later on. Luciano, it's up to you now.
Yes. Okay.
I stopped sharing.
If there are no questions, I think that I can anticipate the time, and moment I have to share the screen. Okay. Do you see the screen? Do you see the presentation?
Yes.
Yes. Okay. So I will present to you. My presentation is divided in 3 parts. The first is about the sensitivity analysis to determine which are the parameters that have a bigger influence on in-train forces. Because as has been mentioned before, when you increase the length, increase the weight of a train consist, you have to face with in-train forces, and you have to be sure that you avoid any derailment risk or disruption risk. The second part is about different possible solutions that implement different radio technologies. So different train consists with 2, 3, and 4 traction units. And the third part is about the Trend-I simulations for the experimental test campaign of Freight Rail 2. This will be in 2021. Trend-I is, maybe you know, a software of the USC, and this software has been tested in the past years against several experimental cases. And also during this project, we have again validated it. So the first thing to do when you want to put in service this new type of train is to consider that coupled trains can behave in a way that is different from already classical trains, classical running trains. And one thing that is interesting is to find if increasing the length of the train, increasing the number of traction units, the number of parameters that has an influence, that have an influence on the in-train forces can change or not. So for this reason, we at the beginning of M2O performed a sensitivity analysis. We had a big number of parameters because many parameters belong to pneumatic problem and others to the mechanic problem. And the aim, as it is written here, is to find the most important parameters to identify interactions among parameters and to see if these parameters change if we increase the length of the train or the number of traction units. In doing this work, we followed the approach of USC 421. USC 421 is a USC leaflet. There will be in future an IRS, okay, but that advice to investigate the effect of technical parameters on in-train forces. Technical parameters are parameters that are outside the control of value undertaking, but they influence the in-train forces. For example, the exact value of maximum pressure in the cylinder. Okay, this is around 3.8 bar in loading conditions, but the exact value can change. And this change has, of course, an effect on in-train forces. Or we have also the operational parameters, which are under the control of value undertaking. An example of operational parameter is the mass distribution, is the train length, is the technology, the radio technology implemented, the speed, and so on. So in some cases, the difference between technical parameter and operational parameter is not so clear. For example, if we consider the starting speed for an emergency braking, this can be 30 kilometers per hour. This 30 is an operational parameter, but a small variation for which you start effectively the emergency braking is a technical parameter. So we performed several analyses, and here, of course, I can tell you about just few of them, considering dangerous maneuver, so emergency braking from cruising and emergency braking from full traction. These are the maneuvers that usually enhance the in-train forces, and for this reason they have been considered. The first challenge that we had to solve was that it was not possible, it was not feasible, it was also not interesting to perform a sensitivity analysis just on one train, because the freight trains are very different in Europe. We have different type of wagons, different type of payload, different lengths. And so we decided to organize the work considering families of trains. So we have considered three families of trains. So the first family, basic family of train is a classic train with one lock at the beginning. It is the load is almost homogeneous. The length is 740 meters. The second basic train family is made of train realized by coupling two subtrains. The first is 400-meter length and having a mass between 1,200 tons and 1,600 tons. And the third train, the second train, of course, is 300 and so on. The third train family is made by coupling four subtrains with a length up to 1,500 meters. These trains have been generated virtually. Okay, so we have implemented the algorithm of the USC 421 to generate trains virtually, And these trains, these virtual trains, are similar to running trains. Okay, similar in terms of in-train forces, of course. So we have realized the trains, and each basic train family has been characterized with 1,000 trains. And from each basic train family, we have realized a reference train family, which is a train family. So, for example, 2 couple trains performing an emergency braking, or a full traction followed with an emergency braking. And then on this type of trains, we have changed the parameters, the technical parameters, to see their effect on in-train forces. So for each reference train family or target train family, we have a cumulative distribution function. And comparing the area between the two, we were able to understand if the variation of this parameter is good for longitudinal forces or not. In our study, we considered together in-train compressive forces and in-train tensile forces. And so by looking at these areas, we have found a measure of the effect of one parameter or more parameters acting at the same time on in-train forces. Here, there is just an example of results. These are tensile forces, these are compressive forces. This is a train made by coupling 2 subtrains performing an emergency braking. And here you see that we have the increment and the decrement of the parameter, and we see also the effect of the first order. So what happens when we consider just the effect of alone this parameter, or when this parameter is changed together with the other parameters, so the total order. And in green are reported the interaction terms that usually are small. Okay, so each parameter, when one parameter changes, has a big influence, and the interaction terms are not so important. So as you can see here, we have 4 parameters. Here the names are the names that are used in the Trender software. And we have 4 parameters that both in tensile forces and in compressive forces influence the in-train forces. So this parameter is a parameter that of a control valve that governs the first filling of brake cylinder. This is a parameter that controls the time to reach 95% of full pressure in brake cylinder. This parameter is the delay. Before Armand mentioned the fact that the delay that is important for in-train forces is not just the delay of the technology, but it is from the time that we start to vent the brake pipe at the leading loco to the time at which the brake pipe is vented at the guided loco. So this is the control parameter, and this is the efficiency of the rigging ratio. So all of these other results, this is the same train in action followed by an emergency braking, shows that the type of train, the type of parameters that have the highest effect on compressive forces are always the same, and compressive forces are the most important for the derailment risk. And this means that we have a set of parameters that we can use to consider a larger variability of in-train forces. And this set of parameters has been used in the second part of this work on the simulation. So the second part here is it's a part in which I will show you several possible train consists that are safe as already as actually running trains. And this means that they can be put in service without any specific problem. if we consider just the topic of longitudinal compressive forces and longitudinal tensile forces. So these virtual trains have been generated thanks to the database of DB Cargo. From this database, we extracted trains having specific length and specific mass, and we have considered these trains as classical trains at the beginning, so with just one loco in front and performing an emergency braking or a full traction followed by an emergency braking. Under these conditions, we have found that these reference trains have this probability of virtual derailment and of virtual disruption. These are virtual probability because, of course, the trains do not do always emergency braking or full traction followed by emergency braking. This is for sure. And the trains do not experience maximum longitudinal compressive force on a very short radius of curvature. Instead, we have here assumed, on a conservative side, of course, that the maximum longitudinal compressive forces is experienced on a part of the track in which the radius of a curvature is small. Okay, this usually does not happen. So for this reason, you see these very high values that are not, of course, they do not belong to the real world. But we have used this as a reference, okay, because we have done the same assumptions also for coupled trains or trains with a distributed power system. And okay, the admissible value of longitudinal compressive force is computed using the RC421. Instead, for tensile forces, we have used a value of 550 kilonewton, which is not a value that can cause a train disruption, but it can damage the train. So it is good to have trains that have longitudinal tensile forces lower than this value. So before showing to you the results of various train consists, I want to quickly show you some results of this further validation of Trendai software. This test campaign is the FFL4E test campaign of May 2019. In this pictures, the solid line refers to experimental measurements, the dashed line to Trendai software, so to simulations. Here you see the traction forces. In this specific maneuver, the train is accelerating. Then it is simulated, of course, a loss in the radio link. So the guided locomotive reduces the power. And after some time, it is commanded an emergency braking from the leading locomotive. So this is the particular maneuver that is tested here. And here, this is the speed. Here, it is reported that the pressure in brake pipe and pressure in brake cylinder. Again, there is very good overlap. And here, there is the longitudinal compressive forces. These are the instantaneous forces. And you see here the difference between the experiments and the numerics. I have similar slide, but it is not useful to comment them. This will be just shown. These are in deliverable already published. And the only thing that I want to say is that we have used the time from the leading to the guided, okay, to have a feeling, not from this type of test, to have a measure of the delay in the activation of the brake pipe, because this is the input parameter for the in-train forces. So as Armand already said, this 1.6 seconds of GSM-R was measured on FFL4E tests, okay, and we have used it in the simulations. So here you see an example of possible train consists that can be realized with one loco at the beginning and another at the end, where you can arrive maximum here to 1,100 meters. This is what we have tested. And in green, you see the good train configuration. Train configuration good means that the probability of virtual derailment or probability of virtual disruption are lower than the probability of virtual derailment and disruption of running trains. And so here you see also the reference to the deliverable. In yellow, you see some other train configurations that were not tested, but they should work. Okay, and as I said before, Armand will again show the use of these possible train sets. Okay, in this next slide, instead I couple two trains. So again, we have just two traction units, but the train is the two trains are coupled. So usually this type of trains exists already, but they have two drivers. Instead, here we use the DPS technology. Instead, this type of trains usually they don't so they don't run on the freight network in Europe. So these trains, also for these trains, it is possible to see the various combinations of length and Howland mass of the first part and the second part that allows low values of in-train forces or high values. So in that. Again, continuing this type of presentation, here I show you what happens if we couple three trains. Okay, here it is we used the GSM-R and LTE radio, not considering the limitations, the problem, the practical problem that Armand has mentioned. Okay, we are just using GSM-R and that's all. This is just simulation, and you see also this S. S means that we assumed, this is just again a simulation, that if you command the braking from the leading loco, but you bend actually the brake pipe with a certain delay, the result is that the brake pipe of the train is vented in an almost synchronous way. So this is a way to improve the system, but of course this has a lot of things that has to be done on the side of the loco. It's clear, this is just a simulation, but it shows that this is a way to improve the performance. So here you see the length of each subtrain, the average length, and here you see the mass. Here are reported the mass intervals of each subtrain, and you see that there are several possibilities that are within these boundaries, that are the boundaries of actual trains, so compressive forces and the tensile forces. So these trains are not safe. Also, these trains are safe. Here we have 4 traction units with the last traction unit at the end of the train. Again, as you see here, we are able to increase the length. We can arrive up to 1,500 meters easily. And we can increase also the hard mass. Again, of course, there are some good and consist and some others that have higher general compressive forces. This 5G is a step towards the next standard FRMCS. Okay, so we have considered a very, very low delay in the communication. And this last slide about the simulations considers 4 trains coupled together with different technologies. And when you couple 4 trains together, what you can see from these lines, for example, is that it is not always the best solution to couple 4 similar trains. You see here the length of the 4 trains is similar. and the mass is similar. But if you couple trains having the same overall length, 1,500 meters, but with the first train longer and heavier, the second train a little shorter and a little lighter, the performance are better. So this means that for the future, there is still the possibility to optimize trains with multiple traction units, with 3 and 4 traction units, adjusting the mass and the length of the different subtrains if this is convenient for the railway undertaking, of course, because maybe it is not convenient. So this really depends on the way it is formed, the train. Okay, so now I go to the last part of my presentation. So what it is important to say is that previous trains have been generated considering overall Deutsche Bahn database. So several hundred thousands of trains at our disposal. We have selected wagons from trains having a specific length and hard mass to build according to the flowchart of USC 421 virtual trains. Now I show you again virtual trains, but considering a restricted part of the database. Now we have just selected all the trains that run from Kronach to Popstella, that are the 2 stations on the track for the test campaign of May of next year. And between these 2 stations, there is also an important variation. There is this slope variation. So the gradient can arrive up to 27 per mil. And in this case, what we have done, we have generated trains, and on the same train consist, we have just changed the technology. So before, it could happen that the type of wagons, the length of the different trains could be different in the previous comparison. Now, everything is the same, except the fact that the loco is classic, or it implements the DPS concept. And as you see, we have tested 3 types of DPS train consists. So with loco at the beginning and at the end, which is the natural evolution of what it is already running, because on this type of track, Deutsche Bahn has this type of train with 2 drivers, or we can couple 2 trains, or we can have 3 active traction units. And for this test campaign, we have tested much more train operations. Because of course, you don't do all the time emergency braking or emergency braking after full traction, of course. And so we tested also other train operations, knowing that these train operations were less severe in terms of in-train forces, but they showed that they were important to check some features of distributed power system. So here you see the nominal behavior. Nominal means that the radio link between the traction unit is active. And here you see 2 train operations in which I will show results just on this, on which the radio link is lost before the new operation is commanded. For example, as the result that I have commented before, you are performing a full traction, then you miss the radio, and actually the system, after some time, reduces the power at the guided loco. And then it performs an emergency braking. So this communication loss occurs before the new maneuver. Instead, in this case, we consider that the radio communication is lost at the same time we perform the new maneuver. So we perform the emergency braking from the leading loco, and at the same time we miss the radio. So the distributed power system is able to detect a pressure drop at the guided loco, and it vents the brake pipe in a safe way. And last, we have also this train operation in which we have the emergency braking commanded in a not wanted way by a guided lock. Okay, so these results refer to nominal mode, so situation in which the radio link is on. This is just an acceleration, then cruising, full service braking from cruising, and emergency braking from cruising. Here you see the maximum compressive forces and maximum tensile forces in the reference system and also in the DPS system. So you see that with DPS system, the compressive forces are lower than in the reference system. Sometimes you can have higher tensile forces, like in this case or in this case, but these values are of no concern. In this maneuver, instead here we check, we simulate a full traction up to 30 kilometers per hour always, and an emergency braking. Here you see the cumulative probability of the reference system and of DPS trains. As you can see, the compressive forces of the reference system are much higher than the DPS system. So it means that the reference system is more dangerous than the DPS system in nominal mode. The other results will show that this is true also for degraded mode. Here I represent the results in a different way. So in this type of degraded mode, we have full traction, then we have a communication loss. So after, today it is 2.5 seconds, but we have showed that even if this time is increased up to 10 seconds, there is no big effect on in-train forces. So the availability of the system can be improved, and this will be tested, of course, in next year. So we have this communication loss, and then an emergency braking is commanded. Here you see two types of graphs. So the first refers to a stepwise reduction of pressure in the brake pipe. So this is the normal behavior of DPS now. Before, with the former Marathon project, we had full service braking application, and this is also a parameter that can be activated in the DPS. We will test it. You see that if it is performed a full service brake application, the compressive forces are lower. Okay, you see now here it is the reference system in step Y. Okay, and you see that each point here, each circle here is the maximum longitudinal compressive force of a single train. So the fact that the points are on this part means that the reference is always more dangerous than the DPS train. In this case, we compare two DPS solutions, and we see that the stepwise reduction gives a little higher compressive forces, but we are simulating emergency braking. Imagine that you, and this is reported in the deliverable, imagine that you perform after the full traction just a first time brake. If you apply a full service brake, you have very high tensile forces. So this is not a good solution. So the actual solution of DPS with stepwise reduction is a good solution. And this is a similar degraded mode, but the emergency braking is commanded at the same time there is the radio link lost. Okay, the radio link is lost. So again, the forces are a little different, but again, the reference system has higher in-train forces with respect to DPS. And again, we can repeat that there is small difference between stepwise or full service brake. Next results refer to a not planned emergency braking. Okay, it can happen that for any reason the second traction unit commands an emergency braking. We have simulated this very unlikely scenario in a condition which is, of course, very rare, which is very unlikely to have radio link loss. Okay, so the radio the two traction units cannot communicate. So the DPS has to detect the pressure and it has to vent the brake pipe. So if the emergency braking is commanded from cruising, you see that again, the reference system or the DPS system is safe at least as the reference case. In this case, we can have higher compressive forces, but they are small, they don't reach 200 kilonewton. Instead, in this case, when this not planned, not wanted emergency braking is commanded from the guided loco, we can have higher tensile forces, but again, the tensile forces of a reference system are bigger than the tensile forces than we have in the APS system. In this case, you see that if the emergency braking is commanded from the second traction unit or the third traction unit, of course, it has an effect on the internal tensile forces, really, but the forces are always lower than the reference case. Then here I show you just one result as an example of the simulations done on uphill, downhill. So here the train is accelerating. Then when the loco in the beginning and the head of the train reach this point, so 30 kilometers per hour, an emergency braking is commanded, or parametrically when the loco is here, an emergency braking is commanded. You see that if you change the point, there is a change also in the internal forces, but always the DPS system is better than the reference system. Last result that I want to show you on this type of trains is about the stopping distance. Again, we have looked at if the fact that we reduce stepwise the pressure in brake pipe can increase the stopping distance with respect to perform a full service brake application. Yes, it increases the stopping distance, but the stopping distance will be always lower than the reference system, always, of 0.5%, but it is always lower. Or it can be even lower of 4%, 5%, or it depends if you perform a full service braking, 9% with DPS with respect to reference system. So again, this solution of applying a stepwise reduction is a good solution because it does not stop the train if the driver does not want to stop the train. It does not provide excessive longitudinal tensile forces, not high longitudinal compressive forces, and also stopping distance are respected because they are lower than the reference system. And then just to conclude, we have this like cherry on the cake. So we are repeating the previous simulation exactly on the train consist that will be tested in 2021, so next year. So here we have wagons that have been selected to be tested, and we have just permuted the wagon. So here the train length and the train mass, it is always the same. In the previous slide, the train length was between 720 and 740. The train mass was between 1,800 and 1,850. Instead, in this case, everything is the same. Just we can appreciate the effect of randomization of mass. This is full traction followed by emergency braking with the radio link on, but with a long locomotive braking regime. These are the results that we have already seen. These results were in G regime. Okay. So as you see, they are similar. Again, the reference system is more dangerous than the DPS system, and this is again true if there is an interruption of the radio for any reason. Of course, the forces changes, they increase, but the DPS is better than the reference system. Because also in the reference system can happen that there is no connection between the two drivers. So the driver on the second loco cannot be aware of what it is happening on the leading loco if there is no phone call, okay? No direct connection between the two. So these are the conclusions of this presentation. I've shown to you some results from the sensitivity analysis, from which we were able to find the most important parameters that affect interim forces. We have found several pre-configurations that can be put in service in a very short time, because we have found several options with GSM-R with 2 traction units. So this is for sure a good news for the market, for the stakeholders in general. And I've shown also to you many train operations for the experimental test campaign of Freight Rail 2 partners of next year. The DPS is always better than the reference system, and when this does not happen, the compressive forces are of no concern. It means that they are lower than the admissible values. As I said, we are performing other simulations, but these simulations are confirming the above conclusions, so nothing new, okay? So thanks a lot for your attention. Okay, so this is, I stop, and I don't know if you have questions. I've not seen nothing here. Or if you want to say something directly, stop the sharing. I don't know how to do. Sorry. So you are speechless. I hope that you found the presentation interesting. Yes. Because so the question is effectively we have wrapped up to. So what I've showed there are instantaneous forces. Instead, what I've showed are 10 meters longitudinal compressive forces, but the train of FFL4E was heavier, much more heavier. Okay. Instead, now the trains that we have simulated, they were less heavier. They arrived, as I said, to 1,850 meters. So this is a reason for why we had lower longitudinal compressive forces. Are there other questions or curiosities? Okay.
Luciano, short
Yes.
remark from my side.
Please.
Niels Weigel, DB Cargo, Freight Rail 2. Perhaps to all that you understand what we plan really in next year in February. I will show this at the end, but as Andrea said at the beginning, we will make now the next step to the somewhat inhomogeneous train traffic sector like single wagon, etc. Therefore, the test train will be much lighter than the train in Freight Rail in FFL4E, and we really want to look at this gradient topic as Luciano showed. Therefore, we selected this very steep infrastructure section, the Frankenwald Rampe in Germany between Kronach and Probstzella. This is a section between somehow Nuremberg and Leipzig, a very important section for freight, and an example for a steep gradient section. And there, especially there, the distributed power system will help us to run really efficient in an efficient way the traffic over these ramps. But I will show this at the end how we do this in detail.
Yes, and we will also test several parameters of the DPS so that you can continue the work of improving the system, of course. So there will be a very important test campaign planned by Freight Rail 2, and so there will be a lot of interesting things for sure. Okay, is there any other question? No, okay. So if there is no other question, I think that I hope that my presentation was enough clear. I don't know. I think that I can leave the floor to Stefano, so that maybe he is more relaxed in as me expressing his topics. Okay. Thank you.
Good morning to everybody. I'm sharing the screen. It should work now. Okay, so my name is Stefano Larovere from NIR Ingegneria, Italy. Within the M2O project, NIR is in charge of the execution of the safety analysis and safety activities. So this presentation concerns the safety concept of train implementing distributed power system. And mainly we will have a look to the main input considered for the safety analysis in terms of general context, functional model, architecture and internal interfaces of DPS train. We will have a look on the safety activities that have been performed through the life cycle of the system and on the results coming from these activities, mainly in terms of hazardous condition, safety integrity levels allocated to functions, and safety requirement specification and verification. At the end, we will have a look to what is the status of the activities for the experimental test campaign of the next year. So in terms of general context, the pictures in this slide show you the perimeters of the integrated railway system, including DPS train and the perimeter of the DPS train itself. So speaking about the whole railway system, it includes the different elements of the trackside infrastructure, as well as the different elements of the signaling systems, and also the different operations on the trackside and on board equipment. Of course, the DPS train, including the existing systems and the distributed power system with its radio equipment. One of the main input for the safety analysis is, of course, the functional model of the DPS trains. In terms of main functions implemented by the system during the setup of the train and during the train running, each function in the table is qualitatively described. Then it has been defined by a set of functional requirements that we considered as input for the safety analysis provided by Freight Rail 2 project. The other main input for safety analysis is the architecture of the trains, DPS trains, and specifically the characterization of its internal interfaces. So in this picture, you can see the new radio equipment interfaced with the TCMS adapted for DPS implementation. You can see the common brake pipe between the different traction units. And so you can see the brake panels in the leading traction unit and in the guided traction unit with their arrangement. In the leading traction unit, the operation on the brake pipe is performed by the existing brake panel, while the DPS panel monitors the pressure in the brake pipe and, of course, manage the communication with the guided traction units. In each guided traction unit is the DPS panel that manages the brake pipe pressure and so act instead of the existing one. Based on this input, we performed different safety analysis at different moments of the project. And so with reference to the system life cycle and specifically to the V-cycle introduced by the SENELEC standard, we worked on the descendant branch of the cycle, mainly with 3 specific safety analysis plus the additional verification activities. The first step, called preliminary hazard analysis, was focused on the integrated railway system, so all the elements of the within the perimeter previously shown. The objectives are to identify a first list of hazardous conditions related to the operation of DPS train, and to identify the element factors of the system that could lead to the occurrence of these hazardous conditions, specifically with focus on the characteristics of long freight trains. And then to specify a first set of mitigations to be implemented by the DPS train as well as by the remaining elements of the integrated system, and so in the setting of the operational context. During the next step, so the hazard analysis, the focus was on the DPS train, and specifically the analysis was focused on the potential deviations from the expected behavior of the system in the execution of its specific functions. The objectives are to identify further hazardous conditions and to specify further mitigations. With the same objectives, the next step was an interface hazard analysis, going through the analysis of the potential deviations in the data signals exchanged between the different subsystems of the DPS train, so through its internal interfaces. So to give you a global picture, we considered different inputs, in part coming from previous experience, from previous projects or previous demonstrators, and then some specific input provided by Freight Rail 2 project and concerning the functional specification and the architecture of the DPS train. Based on this input, we performed 3 safety analysis, a preliminary hazard analysis focused on the whole integrated system, and then the hazard analysis and the interface hazard analysis focused on the DPS train. And the results were collected into a first deliverable of the M2O project, a safety report focused on a generic implementation of the DPS trains, and providing as main results the hazardous conditions to be considered and a set of safety mitigations. Based on these results and going through the safety verification and validation activities, performing some of them and planning the remaining activities, we developed a second deliverable which is focused on the demonstrators for the next experimental test campaign, where safety relevant information produced or collected during the M2O project is provided through a structure compliant with the typical content of a safety case as defined by the SENELEC standard. So, based on this process, we will have a look to the main results obtained. First of all, in terms of hazardous conditions related to the DPS train operation. And we are referring to both specific hazards that are strictly related to the characteristics of the DPS train, as well as to conventional hazards that generally apply to freight trains, but whose risk can be increased because of one or more characteristic of the DPS trains. The basic assumption is that for the remaining conventional hazards, there are proper mitigation through the existing technological and procedural provision. And here you have the second part of the structured list of hazardous conditions. These hazards has the potential to produce catastrophic consequences according to the definition provided by Senelec standard. And we identified the main accidents that can be produced by the different hazards and the consequences, the potential consequences of these accidents. We used two safety integrity levels by simplifying a bit the formal approach defined by the Senelec standard. And specifically, a high safety integrity was required to the functions that could lead to hazardous condition, and that can guarantee a frequency of occurrence of hazardous failure within the limits stated for SIL4 application. A low safety integrity has been required to the function that could lead to hazardous condition, but guaranteeing a frequency of occurrence of hazardous failure within the limit for SIL2 application, and in these cases specifying additional operational mitigation that of course should be able to avoid the event and to put and maintain the system into a safe state. They shall be effective and they shall be reliable, meaning that at the end the frequency of occurrence of the catastrophic consequences because of the failure of the function and the lack of additional mitigation should be acceptable. Speaking about the safety requirements, starting again from the three main safety analyses that we developed, we obtain a set of safety mitigations. And these safety mitigations have been classified in different categories as defined in the part 2 of the Senelec standard. And specifically, we have a first set of safety integrity level requirements specifying the safety integrity level allocated to functions and then propagated to the functional requirements. And here in this table, you can see the list of the main functions previously introduced, a brief description of the worst hazardous scenario, and then the safety integrity levels that has been specified for each function, plus the additional mitigations identified and specified to achieve an acceptable risk. The second category of safety mitigations identified during the analysis concern functional safety requirements, defining the expected behavior of the system in terms of functional operation, detection of single faults, and action following detection. So just to give you some example, speaking about the correct functional operation and by referring to the emergency braking, this safety functional requirements describe what is expected to the leading traction in terms of application of the emergency brake locally at the leading traction unit and sent over the emergency brake command to hold the guided traction unit of the train. Then they define what is the behavior of the guided traction unit when an emergency brake command is received, but also when, in case of detection of any condition locally in the guided traction unit requiring the train stop, shall act, and so cut off the traction, vent the brake pipe, and communicate to the leading unit the emergency brake request. So how the system shall work normally in failure-free condition. Here we have an example of safety functional requirements concerning the detection of radio communication loss. And specifically, we asked for a continuous exchange of messages for the implementation of a live sign, and we define which are the conditions for which the radio communication shall be considered interrupted, and also the information that shall be provided to the driver. The third set of functional safety requirements concern the reaction to fault, and here some main examples concerning the reaction to the loss of radio communication, mainly to the completion of some ongoing action or the cancellation of other ongoing action, and the reaction to a degrees of the brake pipe pressure. And in this sense, it is required that each traction unit cut off the traction when the brake pipe pressure is below a defined limit, independently from the status of the radio connection. And so by implementing a real redundant way to apply braking when required by the leading unit. And specifically to ask when this reduction of brake pipe pressure is detected, to cut off the traction and to vent or assist to the venting of the brake pipe. Of course, independently from the radio communication status, as said, in order to guarantee the brake automaticity, but extended on the whole length of DPS train. Going on the third set of functional of safety requirements, we have technical safety requirement. And in this category, we are referring to the compatibility between the DPS train with the track, and so different characteristics of the train as well as of the specific tracks are involved. We are also speaking about safety-related application conditions that can be exported to the DPS train from the signaling system and the train detection system. And we are speaking about the longitudinal train dynamic studies. And so the discussion previously made by Luciano. And specifically concerning this activity that is within the perimeter of the M2O project, we have different mitigations describing what is required to simulation. So which kind of simulations should be performed, covering which kind of condition, and then providing guide for a validation of the activities that have been done. The last set of requirements concern procedures for staff, procedures for the driver, and include both the existing procedures and some specific procedures for some specific topics to be defined with specific reference to DPS train. And the different safety requirements clarify which kind of existing procedures could be used and which specific procedures should be defined. So based from this set of safety requirements coming from the safety analysis, we define the set of verification activities to be performed for a safe execution of the experimental tests planned for the next year. And they include functional tests in order to verify the implementation of the functional safety requirements, some specific activities concerning the verification of the technical safety requirements, and specifically about the compatibility between train and track, the fulfillment of the safety-related application condition applicable to the DPS train, and as said, the LTD studies. And then the specification of the instructions for staff and driver, providing the references to the existing procedures or the specific procedures defined. Looking beyond the execution of the experimental tests, and so thinking to the activities for future certification, they have to include both verification and validation on generic products in order to verify the fulfillment of the safety integrity level and functional safety requirement, as well as the verification and validation activities to be performed on each specific applications, mainly focused on the technical and contextual safety requirement. So we focus on the next experimental test campaign, just to summarize which are the main characteristics relevant with the safety. Luciano previously mentioned the maximum gradient of the test track impacting the in-train longitudinal forces. Of course, it is relevant to know that the DPS test train will include traction units that are approved or under approval, and also the vehicles are approved freight wagons. Of course, the length, mass, number of axles, axle load of the DPS test train will not exceed the allowable limits for the test track. As introduced by Luciano, the DPS test train will experience, based on LTD studies, longitudinal forces that are not higher than for the reference system for this specific test track. And also the braking distance is expected to be not higher. Concerning the communication, Armand mentioned the use of the safe data transmission safety layer, the SDTV2 safety layer, supporting safety function up to SIL2, and then consistent with the allocation of the safety integrity level that come from the safety analysis. And also Armand mentioned the security provisions that are implemented for the LTE radio communication used for test runs, that of course are limited in space and time. Speaking about the experimental test campaign, based on the set of safety mitigation, we identified with a certain details the different safety verification and validation activities to be performed, and how evidences should be produced. We are referring to the documentation concerning the test track, concerning the train. We are referring to the test instruction, providing the test specification that provide the instruction to the staff on the different topics addressed by the different mitigation. We are also speaking about two specific M2O deliverables, providing evidences of the high longitudinal train dynamic, and providing information on the radio communication. We are also speaking about additional documents that include the traceability between the functional requirement and the mitigation. We are speaking about the report of the tests to be performed, both functional tests and specific tests as for the antenna interferences, and of course on the existing documentation concerning the existing equipment on board. As you can see, we are contributing to these evidences mainly with the studies on the longitudinal train dynamic and on the radio communication, while the remaining evidences will be provided by FreightRail 2 project, working through the different mitigation that specifically request for specific evidence. So by summarizing, the safety analysis have been performed on DPS train within an integrated railway system. And this safety analysis provided a set of hazardous conditions related to a, let me say, generic DPS train operation, a set of functional safety requirements to be implemented by the DPS train, a set of requirements supporting the planning and execution of the LTD simulation, and a set of safety-related application conditions to be exported to the remaining elements of the integrated railway system. All these results are provided in a dedicated deliverable of the project, and they are the basis for the safety demonstration of future specific applications of DPS trains, where we are referring to a specific application in terms of a specific train or train family and tracks where the train should run. Of course, it includes the next experimental test campaign and future applications. Specifically on the next experimental test campaign, verification and validation activities have been defined in order to provide evidence of the implementation of each safety mitigation. And as said, they include the LTD simulation performed under the M2O project, specifically the one focused on the demonstrators, consistently with the safety analysis performed, plus further evidences to be gathered by FreightRail 2 project and concerning mainly the compatibility between train and track, the instruction to the staff and driver, the traceability between the safety mitigation and the last version of the functional requirements and tests, and the report from the performed test before the experimental campaign. As said, this safety relevant information produced and collected during the M2O project is provided by a second deliverable structured in compliance with a specific application safety case as defined by the SENELEC, of course with some limitations related to the development of the activity within a research project. And specifically as intrinsic limitations, no formal verification and validation process has been performed nor planned for the specific DPS developments and integration within the existing traction unit. And no reference to generic product safety case is available. So based on this intrinsic limitation, some additional safety-related application conditions are specified in order to assure a safe execution of the experimental test campaign, mainly asking for personnel attending each guided traction unit equipped with an independent way for communication with the driver in the leading traction unit. And as introduced by Luciano, we are now verifying if this personnel shall have responsibility on the brake application or not. And in the first case, of course, the personnel shall be aware of the execution of the tests and of the intervention criteria and required reactions. And that's all from my side. Thanks for your attention.
Okay, so now the floor is for Tuf, for Paolo, and maybe we leave some time for the questions after. Okay. Paolo, you can share your screen. Maybe Stefano, you should stop sharing your screen so that Paolo can share his slides.
Done.
Yeah, good morning, everybody. I hope you can see my screen.
Yes, yes.
Very good. So again, good morning, everybody. I'm Paolo Gianotti, working for TUSUD, and I will be presenting the result of our activities for M2O together with the colleague Dirk Thomas, who is an expert for running dynamics and for the evaluation of the simulations performed by Luciano. We are in charge of work package 4 in the M2O project. Sorry, my mouse is moving too fast. We are in charge of work package 4, which is an assessment task. An assessment task is required by by all the safety approval processes for the authorization of a commercial service of railway systems, and it's in a way the execution of an independent evaluation of the safety demonstration, who in this case for this project has been put together by Stefano as described during his presentation. So for the assessment, we received the inputs from the other work packages. Work package 2 was the one described by Luciano for the running dynamics part, and work package 2 was one described by Stefano regarding the safety analysis, and work package 3 is the one described by Luciano for the running dynamics part. We are putting things together, and so our tasks start with the assessment of the risk analysis, start with the assessment of the safety analysis described by Stefano during his presentation, and then we split a little bit because overall the safety analysis derives on aspects related to functional safety and on aspects related to running dynamics. At the end, we put things together and provide an overall result based, again, on the conclusions put together by Stefano as described during his presentation. Which are the reference standards for functional safety? I don't want to spend too many words on this. We have a set of standards. The most important one is 5126. Which is related to the demonstration of reliability, availability, maintainability, and safety. And then we have more specific standards which are related to the safety demonstration related to hardware, software, and communication systems. We will see how we took care of this during our activities. The overall assessment plan is consistent with the B cycle as defined in the 5126 standard. The B cycle starts with the definition of the concept of a new system and develops through a risk analysis into the specification of system requirements, allocation of requirements to the subsystem levels. Then, of course, we have design and implementation, manufacturing, integration, validation, and then system acceptance, which is the final goal for achieving the authorization for commercial service of any new system in a railway environment. So our tasks are to evaluate how this process was put in place, to evaluate the simulations described by Luciano, and to assess the operational scenarios which were simulated by Luciano. At the end, our objective is to generate an overall ISA report, an overall independent safety assessment report, which will hopefully support the authorization in later phases of the project. How have we achieved these tasks? We have been reviewing the input documents created basically by Luciano and Stefano, and we have been continuously involved in the technical meetings for discussing the progress of the project. This is a research project, so it's of course not yet a real project. So there are some peculiarities which need to be taken into account. The 5126 standard requires some independence to be put in place between the various roles and defines a very well-defined safety organization to be put in place. This being a research project, of course, we could not demonstrate compliance to all of these requirements. Then the second peculiarity we have is that, as anticipated by Stefano, we lack at this stage of the project the safety demonstration related to the generic products. During their presentations, Luciano and Stefano described the overall architecture. So we basically have a control part and, let me say, a mechanical part of the problem. The control part is covered by functional safety, and it must, from a functional safety point of view, we must prove that the brain of the system, the brain of the system consists of the communication system, and on the interfaces between the radio communication system and the train equipment, which will command the brake application and the traction application on the guided locals. These underlying building blocks, which at the end are part of the brain of the system, do not have at this stage a complete safety demonstration, and this shall be taken into account when providing a final opinion regarding the safe execution of tests. And then the third limitation we have is that we are limiting the analysis to one single configuration of locals, and in this way reducing the scope of the validation to the specific application, which is the one that will be tested in 2021. I mentioned that we are taking into account the brain of the system and the body of the system. So we have an interaction between functional safety, how good is the brain, and running dynamics. That is, how safe is the body of the system. I mean, the mechanical layout of the train, and all the considerations made by Luciano regarding tensile forces, compressive forces, and so on. These two words are of course intertwined. So what we are making sure is that all the functional safety characteristics which are relevant or influenced by the dynamic behavior of the body of the long train are validated by simulations or tests in all pertinent operational scenarios. And this leads us to the three most important points in our view related to this interaction. Reaction times, which are one of the most important parameters which Luciano described in his presentation. Achievement and retention of safe states, which will be responsibility of the onboard control systems when the safety demonstration will be available, and degraded modes of operation, such as loss of communication or failure in the control system. This is it for the interface. Regarding the analysis of running dynamics, I give the floor to Dirk for providing an overview of our assessment tasks related to the running dynamics.
Thank you, Paolo. Dirk Thomas is my name. Good morning, working for TÜV. Been working with the longitudinal train dynamics here, the assessment of this. As Paolo indicated, the function safety and the random dynamics, they're somehow interacting. When we have a train running with DPS, we need to make sure that we respect the longitudinal dynamics and the derailment risks that might be imposed, concrete by limiting the longitudinal compression forces that are related to derailment risks, and also controlling the tensile forces in longitudinal direction to a safe level. And the functional safety characteristics, they need to ensure that we have a safe run, the running safety is ensured, but at the same time they may not either jeopardize the running safety. And that's, of course, when it comes to both nominal condition and degraded modes for the DPS. And the assessment that we've done is based on the available deliverables that get during the project, which included the validation of the train day simulations with measured data, configuration of critical parameters that resulted from the sensitivity analysis, which is, for example, the filling time of the brake cylinders or the brake efficiency, the results of the identification of possible train families that can be operated safely with DPS, communication technologies that can be involved with DPS, meaning here we've talked about GSM-R and LTE, but also simulations have been done assuming 5G technology. The infrastructure characteristics that's implemented, meaning the minimum curve radius and the topography of a test track, for example, that was shown before, that's important. And also a representation of degraded modes, for example, when you have communication losses, and implemented countermeasures to handle these degraded modes then. If you go to the next slide, Paolo. And based on these ones, if we have concern critical traction and braking maneuvers that Luciano showed in his presentation, these ones were taken into account, and we compared to a non-DPS reference system that's running today. The train consists that can operate with safety with DPS on communication by GSM-R can be identified. And the number of possible train consists can be increased using LTE. So there's the difference between GSM-R and LTE can make it possible that when we use LTE, train consists that maybe can run safely with GSM-RA, they can be run safely with LTE. Or even if we go to 5G in the future, but that is more in the future, but 5G has quite potential there. With the DPS in nominal mode, the train performs at least equally safe as the reference system when it comes to LCF, I mean the derailment risk. For degraded modes in communication losses, implemented countermeasures are capable of keeping the LCS to at least the equal level as for the reference system. And the track topography, which was included in the analysis as well and has been assessed, the communication loss might result in a worse behavior than compared to the reference system, but then this is in uncritical levels of LCF. So this somewhat worse behavior is not critical here because we are in LCF levels with in uncritical levels. The assessment with respect to the coming demonstrator next year with respect to running dynamic simulation is at this stage ongoing. Paolo, may I get back to you?
Yeah, thank you, Dirk. So we come back to the description of the analysis performed for functional safety. We are a little bit late, so this set of inputs which have been receiving was already described by Stefano during his presentation. In a nutshell, we have assessed the preliminary hazard analysis and the interface hazard analysis, which led to the definition of the safety countermeasures, which have been described by Stefano. The overall appraisal for the overall result of our assessment task is that, as we said, the safety analysis have led to a set of countermeasures, and the processes in the other work packages to carry out the safety analysis are adequate and in line with the requirements of the applicable standards. Regarding communication, from a purely functional safety point of view, there is no difference between GSM-R and LTE, provided that a safety layer compliant 5159 is implemented. Of course, the implementation of the safety layer shall or can include the advantages in terms of